Welcome back, class, and today we are going to continue with Chapter 3. Here we go. And so we're going to talk about polynomial functions, graphs, applications, and models. Okay? So these are all the things we're going to talk about in this video. So now, as with quadratic functions, the absolute value of a in f of x, ax to the n determines the width of the graph. Okay? So if we have this type of function, okay, the coefficient here of x of n determines the width of the graph. So when the absolute value of a is greater than 1, the graph is stretched vertically. Okay? So that means up and down. Okay, so it makes it narrower when that happens. If a, the absolute value of a, is between 0 and 1, then it's shrunk, which means it is compressed vertically, so squished downward, so it makes it wider. So now if we look at other characteristics, so that's one characteristic, so this is again the leading term, right? So compare the graph of this basic polynomial ax to the n with the following. F of x equal to negative ax to the n is reflected across the x-axis. The graph of f of x of ax to the nth power plus k is a translation. It's translated k units what? Up. Okay? If k is positive. Okay? Or k units down if k is negative. Okay? So the graph of this one, now notice that we're subtracting h inside the function. So now this is going to be a translation in the horizontal direction, right and left. So it's going to be right, okay, if h is positive, and it's going to be to the left if h is negative. And then we have both of these together make this a translation. It's a combination of the translations going left or right or up and down. Okay, so if we look at this function here, determine the largest open intervals of the domain over which each function is increasing or decreasing. Okay, so we want to find the intervals for this function where it's increasing and decreasing. Okay, and if you look at this function, look at the graph. Okay, so here's the graph. So where is it increasing and where is it decreasing? Now, when we determine that, we're going to go left to right. We always go from left to right when we're reading these graphs, if you will. So if we walk and we look left to right, this is what? It starts down here, way, way, way down here, and it continues to go what? Up, right? And then it flattens out here, and then if you keep walking, it continues to go up. Okay, in fact, no matter how far to the right you go, it's going to continue to go up. So in this case, it's increasing everywhere on the number line. So this would go from negative infinity to infinity, that it's increasing, and which means it's decreasing nowhere. Okay, so it's increasing on the entire domain, which is all real numbers. Now what about this one? Now this is 1 plus x plus 1 to the 6th power. So let's graph this. Okay, now look at this. So this one starts way up here to the left and goes down, 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 down until you get about here, and then it flattens out, and then it goes up. Okay? So now don't be fooled by this. Don't be fooled by this. If you zoom in here, it's not at 0 the whole way across here, and it's only because of the graph. It does flatten out, but if you zoom in on this piece, you'll see that it only intersects the graph at one point, right here. Okay, so don't be fooled by the graph here. Okay, so if we look at the graph, where is it decreasing and where is it increasing? Well, let's do increasing. So where's it increasing? Well, if we go again left to right, this is going down. So as we trace the graph, it's going down, 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 down until here. And then what? Now it's going up, 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 up. So it's increasing from -1 to what? To positive infinity. And is it decreasing? What is it decreasing? On what interval? From negative infinity to -1. And so on the entire domain, it's increasing from -1 to positive infinity and decreasing from negative infinity to -1. Okay. Now, let's see here. Okay, so now here is a function f like that of x to the 6th, but it has this, excuse me, +1. Okay, so it has this +1, which means it's a translation to where? To the left. Okay, and it's 1 unit to the left. Now this function is decreasing from -infinity to 1. Now I would not put the square bracket here. This is incorrect. You do not put the square bracket because at 1 it's neither decreasing or increasing. So we would not include 1 in that. Okay, and we would not include 1 here. Okay, if we're just talking about increasing, decreasing, the interval would go from -infinity to -1 with the parenthesis here, and then a parenthesis here. So at -1, it's neither increasing or decreasing. Okay. Okay, what about the here? Now we've got a couple of things going on. So if we graph this, so we've got a translation in this inside here, so it's moving to the right 1 unit. This is 3 units up. So if we graph this thing, it's going to be up here, right? Normally, if it was just x to the 3rd, it would be right here, right? This would be right here, but again, it's a translation with a reflection, and it's also a stretch, a vertical stretch. Okay, so now, but let's look at the graph. So in this case, again, if you walk from left to right, you start way up here, and it goes down, 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 right? So you're going down, and here it flattens out, and you keep going down. Okay? So this is decreasing everywhere. Okay? So this decreases on the entire number line. Okay, now, unless otherwise restricted, the domain of polynomial functions is the set of all real numbers. Okay, polynomial functions are smooth, continuous curves. What does that mean? Smooth means that there's no sharp edges, there's no cusps, there's no sharp corners. It's just nice and smooth. Continuous means that you can trace the graph. You should be able to trace the graph without lifting your pencil or pen off the paper. Okay, and on the interval from -infinity to infinity. The range of a polynomial function of odd degree is also the set of all real numbers. Okay, but that's only for the odd degree. Okay. Okay. Let's see here. These graphs suggest that for every polynomial function of odd degree, there is at least one real value of x that makes the function 0. Okay, because if the range is all real numbers, and the domain is all real numbers, then there's got to be a number such that you get 0 gives you 0. Okay, or not 0, but you get some x value will give you 0. Okay, so the real zeros are the x-intercepts, like I've said, of the graph and can be determined by inspecting the factored form of each polynomial. So we can factor the polynomials and then use the zero product principle, right? So here we have odd degree, right? So if we have odd degree, this is a odd degree polynomial. This is a cubic function, right? Notice that it intercepts here, here, here. So there are 3 real zeros. Here we have a what? This is a graph that it's an odd graph, and it has 1 0. Okay? So this one only has 1 0. And this one has 2 zeros. Okay? So you can have odd degrees. Notice this one here crosses 3 times. Right here. And notice that we have 3 factors. Here, this crosses once, and this is a cubic function again. And notice that it has 1 real factor. These are complex, and so it has 1. And notice this is a 5th degree odd and has 2 intercepts. Right here and right here. Okay? And these are also repeated. So here's even degrees. Okay, a polynomial function of even degree has a range of the form negative infinity to k. So apparently this textbook puts the brackets. So again, I'm not going to count you wrong if you put the brackets. And bracket here. So the range of values. Okay. Again, since we're talking about the range, we can include k. But again, in the example I was talking about earlier, they were talking about increasing and decreasing. So there's the difference in the nuance there. Here we're just talking about the range. So you would include k in that value. Okay, so it's either going to be this side or this side because it's an even degree. Okay, so here you're going to include k, and the range is either going to go this way or the range is going to go this way. So it's either going to go to negative infinity or it's going to go to positive infinity. If it's an even degree, it will not go to both. Okay, it's either or, but not both. So here's an example. So here's a 4th degree, a quartic. Okay, and notice that it has 1, 2, 3, 4 factors, right? These are all real zeros, and so there's 4 x-intercepts. Here we have a 6th degree polynomial, and notice that it has 3 factors. 2 of them are repeated, and there are 3 intercepts, x-intercepts. And notice that in this case here, both of the end behavior of the graph, both arrows go up. Here, both arrows go down. Okay? If you look at these, the odd ones, one arrow goes down, the other arrow goes up. This arrow goes up, this arrow goes down. So the tails are going in opposite directions. Whereas if it's an even degree, notice that the tails are going in the same direction. Now, the behavior of a graph at a 0 depends on the multiplicity of the 0, how many times it's being repeated. Okay? And that's determined by the exponent. Okay? The exponent on the factor. So it could go through here, going down. It could go through that intercept this way, or it could go through the intercept this way. Okay? And so at whatever that value is, the graph crosses the x-axis at C if the 0 has a multiplicity of 1. Okay? In fact, I can expand this and say it's going to cross the x-axis if the multiplicity of the 0 is odd. So not just 1, but if it's odd. The graph is tangent to the x-axis at a c value if the 0 is of even multiplicity. Okay, so we say it bounces or touches at c. Okay, or turns. But typically I say it either bounces at c or touches the x-axis at c. So the graph crosses and is tangent to the x-axis if c is a 0 of odd multiplicity greater than 1. Okay, so again, this is a nuance that it doesn't really matter, but it crosses. The bottom line is it crosses. As the odd degrees get higher, it gets flatter. So it'll still cross at c, but what happens is it starts to flatten more and more and more at c. Okay, that's really all that's going on. Now the graphs exhibit functions of odd degree and even degree, show that polynomial functions often have turning points, okay, where the function changes from increasing to decreasing, right? That makes sense. Or from decreasing to increasing. So anytime the graph changes direction, it goes from increasing to decreasing, it's going to have a turning point. That makes sense, right? So now we can use that to say, hey, we can figure out what the number of turning points is going to be. Okay, not exactly, but we can say that based on a polynomial function of degree n, we know that it's going to have at most n minus 1 turning points, with at least one turning point between each pair of successive zeros. Right? That should make sense, because if we have two zeros, right, it's got to turn somewhere in between those two zeros in order to cross the x-axis. So if you cross the x-axis one point and you cross the x-axis at another point, it's got to turn at least one time between those 2 points. So now let's talk about end behavior. The end behavior of a polynomial graph is determined by the dominant term. The dominant term is the leading term, the one with the largest exponent, because as x gets larger, larger, and larger, and larger, and larger, this is the term that is going to end up controlling the behavior as x gets really, really, really big positive or really, really, really big negative. Okay, which means end behavior, right, at the tails. So if we look at this polynomial function, we know that this is going to behave like a cubic function. This is going to behave very much like x cubed. So as x gets really big, these three terms become negligible, okay, as far as end behavior. So this is going to have the same end behavior as x cubed. Okay, we can even forget about the 2, but x cubed. Okay, so that means this is going to have tails that go the opposite direction, and it's going to start what? It's going to start low, so it's going to start really negative, and it's going to end over here positive. Okay? So in other words, it rises to the right and falls to the left. So to the left it falls, goes down, and on the right it goes up. So it looks like this. Okay, so what we say is, in this figure here, x increases without bound. So y does also. So in this case, as x approaches infinity, this is the way we write it, as x approaches infinity, positive infinity, y also approaches positive infinity. Okay, and as x approaches negative infinity, y also approaches negative infinity. Okay, just like I said. And then, of course, the factors here tell us where the intercepts are. Now here we have negative x cubed. Okay. The graph in this figure has the same. So this is now what we did was we changed with negative x cubed with a bunch of stuff here, which factors into this. But this behaves very much like negative x cubed. Okay. Well, what is negative x cubed? Well, it's the reciprocal, right? It's the opposite. It's the reflection of x cubed. Well, x cubed goes down on the left and goes up on the right. So the negative x cubed would have the opposite effect. So here it goes up on the left and down on the right. Okay, rises to the left, falls to the right. Or in other words, as x gets really large negative, as x approaches negative infinity, y approaches positive infinity. As x approaches positive infinity, y approaches negative infinity. Now, look at all of the things we can do. So we can take all of these characteristics and put them together. Okay, so we can say, suppose that ax to the n is the dominating term of a polynomial function f of odd degree. Okay, so if a is greater than 0, then as x approaches infinity, positive infinity, so does the function. And as x approaches negative infinity, so does the function. So as x goes to negative infinity, so does y, okay, or f of x. Therefore, the end behavior of the graph is going to be of this type. It's going to rise, right? It's going to go from falling on the left to rising on the right. So it's going to have this general increasing trend, if you will, okay? If we have ax to the n with odd degree and a is negative, then it's going to go the opposite direction. It's going to flip, which means it's going to have a general downward or negative trend, right? So if this is negative, it's going to have a general negative downward trend from left to right. So it's going to look something like this. Okay, so these are the characteristics if the degree of the polynomial are odd, and a is positive. It's going to have a general positive trend from left to right. And if it's odd degree with a negative coefficient on the leading term, a is negative, then it's going to have a general downward trend from left to right. Now, what if it's an even degree? Well, if it's an even degree, like I said earlier, the tails are going to go in the same direction, which means they're either both going to go up or they're both going to end up going down. And so if a is positive and we have an even degree, both tails go up. If we have an even degree polynomial and a is negative, then the tails both go down. Now, based on what we just talked about, let's figure out what the end behavior for this graph is going to be. Well, the only thing we need to look at for end behavior is this one. So which one of these do you think behaves like this one? Well, what do we have? We have an even power, even degree, and a here is positive 1. So that means that the tails are going to go in the same direction, and the coefficient tells us they're both going to go up. So the only one that fits is C. Now what about this one? Now here we have even degree, so that's the largest exponent here. So even degree with a negative a, right? So this is negative 1, so this is negative, a is negative, and the degree is even. So that means they're both going in the same direction, but they're going downward. And so the answer here would be A. A is the only one that makes sense. Now what about this one? Now here we have an odd degree, and the coefficient is positive. So odd degree means they go in opposite directions. The coefficient here is positive, which means it goes in a general upward trend from left to right. So that means that it's going to be this one. Okay, so it's going to go down to negative infinity on the left, up to positive infinity on the right. And now here we have another odd degree, but this time the coefficient is negative. So this means it's going to have a general negative downward trend from left to right, and the tails are going to go in the opposite direction, so this one has to be D. So here's the graphing techniques that you're going to use. So putting it together for graphing techniques, so if we have a polynomial, so again, these are several characteristics that we're going to use to put together to help sketch the graph of a polynomial. Okay, so a comprehensive graph of a polynomial function will show the following characteristics. We're going to want all x-intercepts, all the zeros, and the behavior of the graph at each one of these zeros. So that's where the multiplicity is going to come in. That's where the zeros are going to come in, okay, to find the x-intercepts. And then do they bounce at the zeros or do they cross at the zeros? That's where the multiplicity is going to help us. Then we want to find the y-intercept. Then we're going to look at the sign. So the sign of f of x within the intervals, right? So we're going to look at the intervals between the x-intercepts. And we're going to find the sign of f of x. Why? That's going to tell us if we're below the x-axis or above the x-axis. Okay? And then enough of the domain to show the end behavior in examples 3 and 4. Okay? So we sketch the graphs of two polynomial functions by hand. So we use the following general guidelines. Okay? Let f of x be a polynomial function where the leading coefficient is not 0 and have a degree n. To sketch its graph, you're going to find all the zeros of f. Okay, so that's step number 1. Find all the zeros of f. Plot them as x-intercepts on the x-axis. Then step 2, find the y-intercept by setting x equal to 0, and that's going to always be the constant term. Okay, the constant term, if x is 0, all of the other terms except the constant term. So the y-intercept is always going to be the constant term. Okay, so it'll be 0 comma a sub 0. And then step 3 is you're going to use end behavior, whether the graph crosses, bounces on, or wiggles through the x-axis at the x-intercepts, and selected points as necessary to complete the graph, right? You're going to have points, test points to see whether the graph is above or below the graph, and turning points and things like that. Okay, so let's use this one as an example. Okay, so here we go. First thing we're going to do is let's find the x-intercepts. Okay, so we use the possible rational zeros theorem. So we're going to use these as our possible starting points, and we're going to use synthetic division to find whether they're zeros or not. Okay, so let's go. So we start with 1. Okay, now remember this shortcut. You can use synthetic division, but with 1 and negative 1, you can use a special shortcut. If you want to find out if 1 is a 0, all you have to do is add up the coefficients. If the coefficients add up to 0, then 1 is a 0. So in this case here, 2 plus 5 is 7, minus 1 is 6, minus 6 is 0. And so therefore we get a 0. Okay, so now that's how you test to see if 1 is a 0. Of course, you get 0. Okay, so if you add up the coefficients and the coefficients add up to 0, then 1 is a 0 of the polynomial. Now, what about negative 1? Negative 1 is very similar. All you have to do first, though, is change the signs of the coefficients for only the odd powered terms. So for 3, you would change this to a negative 2. And for this one, you would change this to a positive 1. and then you add the coefficients. If that sum is 0, then -1 is a 0. So in this case, you would have -2 plus 5, which would be 3, and then you would have 1, which would give you a 4, and then -6, which does not give you 0. So we know that -1 is not a 0 of this polynomial. Now, also, here 1 turns out to be a 0. Now, the next thing to do is try 1 again. So here's your new polynomial. So you've got a factor. So here this tells you x minus 1 is a factor. And this gives you the other factor. And this is the one that you're going to use to divide again. And so if 1 worked the first time, it might work again. So you stick with 1 until it doesn't work. And once it doesn't work, then you're done with 1 and you'll never go back. Okay, so 1 is a 0, so we got a 0 at 1, but now it may be a repeated root, right? It might have a multiplicity of greater than 1. So now, here's what we have. Now we're going to use this one, and now in this case here, we don't have to do synthetic division because it's a quadratic, but if you had a higher degree, then like I said, you would just use 1 again. But in this case, we have many other tools to factor this quadratic. So, so here's the end result. Okay, so here now we can solve these using the zero product principle to find the x-intercepts. Okay, so at this point we have an x-intercept at 1, an x-intercept at -3/2, and at -2. So there are the zeros, and that will give us the x-intercepts here, here, and here. And now the y-intercept, step 2, again, f of 0 is going to give us -6. So we have our y-intercept right here. And so we can plot those. And the fact that it's the leading term for end behavior, it has an odd degree with a positive coefficient. So we know it's going to have a general increasing slope, positive slope from left to right. So it's going to go down this way, and it's going to go up this way. Okay? So now we've got a general idea. Now the only thing we don't know is what's going on in here, what's going on here. So I would suspect that it's going down this way. It's going to go through here, and it's going to go up, right? So you can kind of guess that if it's going up here, it's got to go through this point, because it's got to go through this point. So it's got to go down here, and then it's got to go through this point, so it's got to turn somewhere. Now, does it turn here, or does it turn down here? I don't know. But it's going to go down something like this. It's going to turn, and then it's going to go here. So it has to go through here, and it's going to go down. It's going to go through here. Now, how do we know it crosses? Well, you can think of that it kind of has to cross, because by what I just did, right? But we also know it crosses because look at the factors. All the factors have an exponent of 1, so they have a multiplicity of 1, which means they all cross at the zeros. So we know that it's going to cross here, here, and here. So it's got to go something like this, through here, through here, through here, through here, and then it continues down forever. Okay, so but let's go on. So step 3. Okay, we know that it behaves like this. Okay, and so since the dominating term is this, the graph will behave similar to x cubed, which we already discussed. So each 0 of f of x occurs with a multiplicity of 1, meaning that it will cross the x-axis at each one of those zeros, which we already discussed. Now, because the graph of a polynomial function has no breaks, gaps, or sudden jumps, we know it's going to be a nice smooth curve, and we have all the information to kind of sketch the graph. Okay, now begin sketching the graph at either end of the graph with the appropriate end behavior, and then draw a smooth curve that crosses the x-axis at each 0, and then has a turning point between each successive zeros and passes through the y-intercept as shown. Okay, so now we don't know where it's going to turn, but again, this is just a sketch of the graph. Okay, so it might look something like this. Okay, so it goes through this one, it goes through this one, it goes through here, it goes through here. So it's going to have something that looks something like this. Okay, now if we wanted to get more accurate, we would just plot more points. Maybe some points over here, some points over here, some points here, and some points over here. So, but again, we don't need to, because all we're doing is sketching a general idea of the graph. So additional points may be used to verify whether the graph is above or below the x-axis between the zeros, and add some more detail to the sketch of the graph. Okay, so the zeros divide the x-axis into 4 intervals. So here's where we're going to use the intervals. Okay, so this is one interval, this is another interval, this is another interval, and this is another interval. So we have 4 intervals, and we can pick a point in between these intervals to see whether the graph is above or below the x-axis. In other words, if the function f of x is negative, we know that the point is below the x-axis. If the graph is positive, then we know that that point is above the x-axis. So we can kind of use that as a test point. And if our test point is below the x-axis, then we know that all of the points between the two zeros must also be below the x-axis. Okay? So we want to use some test points using in a table. So let's use this. So we want to try to use test points that are convenient. Okay? So in this case here we got negative 1/2 and 2. So there's not a lot of points here. So this is going to be a point. So in this case here it's going to be difficult to find a quote-unquote easy point to use. So here we use -3. 0 is always a good one to use if it's in the interval, and 2. And so we find that it goes negative, positive, negative, positive. So from negative infinity to -2, it's going to be below the x-axis. On this interval, it'll be above the x-axis. From this interval, on this interval here, it's going to be below, and then on this interval, it's above. And of course, that's exactly what we see, right? So right here, it's below, and then it's above, and then it's below, and now it's above. Okay, so let's look at this here. Now, here they want us to graph this one. Okay, now, here it's a little easier because they already have it factored for us. They already got the multiplicity. So we know the zeros are going to be at 1, 3, and -2, with the multiplicity respectively of 1, 1, and 2. So we know these two are going to cross. So it's going to cross at 1 and 3, and it's going to bounce or touch at -2. And of course, if we look at x equal to 0, we can get the y-intercept, because this will be what? Well, this will be -1, this will be -3, and this will be 2. So this is a negative, negative, and what? Positive. So this is going to be 4, right? 2 squared. This will be 4. 4 times 3 is 12, -12, and then -1 is just going to be +12, and then it's going to be negative. So we end up with a -12, and so the y-intercept is at 0, -12. Also, notice that this is a negative, right? Now, what's the degree? Well, if you look at this one, this has an x, this is an x, and this actually has an x squared, because if you FOIL this out, you'll get an x squared. So the largest degree, or the largest exponent for x, is going to be x squared times x, which is going to give us x to the 4th. So this is an even polynomial, and the leading coefficient is negative. So that means both tails are going to go down. Okay, so we've got the 2 x-intercepts, okay, or excuse me, 3. Yep, 1, 2, 3. And of course, it bounces here. And we got the y-intercept and we got the end behavior. So we've got enough to sketch the graph. And the graph makes sense. Okay, so there's our points, right? There's the y-axis. Okay. And of course, we know that, again, it's going to give us negative x to the fourth, right? Just by what we just did. Okay. And so it's going to go down in both directions. Okay. And then, of course, we're going to, again, step 3, we're going to begin at either end of the graph, and we're going to, with the appropriate end behavior, we're going to draw a smooth curve. We're going to basically cross the x-axis at all of the points, and then we're going to bounce at -2. And then also we know that it's going to change direction in between these two zeros, and it's going to change direction at this zero because it bounces. Okay, and the graph will also pass through the y-intercept at -12. So again, this is the sketch that we end up having. Now, whether this is up here or whether this turns down here, we don't know. Okay, so we know it crosses here. Does this like go down way down here and then come up and cross? I don't know, but this is just one sketch of the graph. Okay, and then of course this splits the intercepts split it into 1, 2, 3, 4 intervals again. So we've got this interval. Hold on a second. Yeah, so we got intervals here, right, in here. So we're going to test these intervals. Okay, so here we could use -3. Here we're going to use 0. And then in this interval, let's use 2. And then in this interval, we can use 4. Okay, and so the points that we get is we get negative. So at -3, it's negative, negative. So below the x-axis, below the x-axis. And then here it becomes positive. So we're above the x-axis. And then here it becomes negative again. So again, this confirms what we suspected. Okay, so now it is possible to reverse the process of example 4 and write the polynomial function from its graph if the zeros and any other point on the graph are known. So we can use the graph to create or go backwards to figure out what the polynomial is going to look like, or what the function looks like. So suppose that you are asked to find a polynomial function of least possible degree having the graph shown. So here's the graph. So we don't know, so again, they give us this, but let's say we don't know this, but all we have is the graph. Well, let's use this graph to find out what we know, right? So the first thing is we know that the zeros, the x-intercepts tell us the zero, so this has a 0 at -2, 1, and 3, right? So that gives us the 4 factors. So we know that this polynomial has to have the factors x minus 1, x minus 3, and x plus 2. Now, here's the thing. It bounces here, so we know we have to have an even degree, right, or an even multiplicity. So we want but again, they want the least possible degree. So we're going to use the smallest value, which would have to be 2. Okay, because it has to be even, but we're going to use the smallest one, so we're going to use 2 here. Now, what else can we get? Well, we notice that the two end behavior arrows go in the same direction. So we know that the degree of the polynomial has to be even. So do we get an even number? Well, we get 2, 1, and 1. So we get x squared times x gives us x to the fourth. Okay, good, we're good there. But the arrows both point down, which means we have to have a negative value on the x-axis. But if we just multiply this x, and this x, we get a positive value. So we're going to have to add a negative to the beginning here. Okay. Now, is this -2, -4? Well, we don't know. So we're going to assume just -1. Okay. So this is a possible answer for this graph. Now, the other thing too is we need -12 here. So it says it crosses at -12. So do we get -12 here? Well, if this is 0 and this is 0 and this is 0, do we get 12? We get -1 times -3, which is 3, times 4, which is 12, and we get a -12. So it works out. We get a -12 here. Okay, now because the graph crosses at 1, 3, and bounces at -2, we know that the factored form of the function is as follows, right? So there's what we just said. Okay, again, why are we using 2 here? Because it has to be even, and we're looking for the least degree. Okay, 4 would work here too, but 2 would be the smallest. Okay, and then of course it has an intercept of -12. Okay, so we know that from the graph. Okay, so now find the value of a by substituting the x and y values of any other point on the graph. So here we can use the y-intercept into the function and then solve for a. So what we do is, again, we have to have an a here. And so we're going to substitute in 0. And this should equal -12. And so -12. And what do we get here? Well, we know what we get here. We get 12. And so what is a? A equals -1. So we now know that it has to be -1, right? So here, algebraically, we figured out that a equals -1. So now we know -1 times this, right? That guarantees that our y-intercept is going to be -12 also. Okay, so we took care of that too. Now, important relationships here. We emphasize the important relationships among the following concepts. Okay, the x-intercepts of the graph y equals f of x, the zeros of the function f, the solutions of the equation f of x equal to 0, the factors of f of x. These are all directly connected, okay? Because the x-intercepts of the graph y equals f of x are also the zeros of the function. And the zeros are also the solution to the equation f of x equals 0, and those also correspond to the factors of f of x. So now, if f is a polynomial function and a is an x-intercept of the graph of y equals f of x, then a is a 0 of f, a is a solution of the equation f of x equals 0, and x minus a is a factor. Does that make sense? So that's how they are connected. Also, the intermediate value theorem for polynomials. So this is a good one. You need to know this one. If f of x is a polynomial function with only real coefficients, okay, so that does include integers, okay, and rationals, okay, so f of x is a polynomial with only real coefficients, which means no complex coefficients, only real. And if for real numbers a and b, the values f of a and f of b have opposite signs. So there's the other part. So first part, f of x is a polynomial function with only real coefficients, and a and b are real numbers where f of a and f of b have opposite signs. Okay, if those two conditions are met, then there must exist at least one real zero between A and B. Because if f of A is positive, let's say, and f of B is negative, then there has to be a point between these two where it crosses the x-axis. In other words, because it's a polynomial function with real coefficients, we know it's smooth and we know it's continuous. So if part of the graph here is above the x-axis and part of the graph here is below the x-axis, then it must be true that there must be at least one point between the two values of x where the graph is equal to 0. So now let's use synthetic division and a graph to show that this function f of x has a real zero between 3 and 2. So let's use the mean value theorem. Okay, so we're going to use the mean value theorem here, or the intermediate value theorem here. Yeah, the intermediate value theorem here. And what we're going to do is we're basically going to use the remainder theorem to evaluate this function at 2 and at 3. So we're going to use synthetic division to do that. Okay, so in this case here, if we use 2, we get a remainder of -1, so f of 2 equals -1, so it's negative. And then if we do 3, we get a remainder of 7, so f of 3 is equal to 7. And do they have opposite signs? Yes, they do. So that means there has to be a number between 2 and 3 such that f of that number, so there has to be some c number, let's say, between 2 and 3 such that f of c equals 0. And that's using the intermediate value theorem. That's it. Now, what if the two numbers we chose gave us the same sign? What can we conclude then? What if we got two positive numbers or two negative numbers? Does it mean that there is no zero between them? No, it doesn't necessarily mean that. In fact, it's inconclusive. We don't know. All we know is what the theorem tells us. The intermediate value theorem tells us what? If these two conditions are met, it's a polynomial function with real coefficients, and the value of the function has opposite signs at the two endpoints of a particular interval. If those two conditions are satisfied, then we know by the intermediate value theorem that there has to be at least one zero between the two x values, the two endpoints of the interval. But if they're the same sign, well, then we don't know. It's inconclusive. Okay. Now, if we want to find the zero, okay, we can use our calculator. And so we use the calculator, and we use the zero function in our calculator to find that the zero is approximately 2.25 on the calculator. Okay, so now we found it. Okay. Oh, and by the way, notice that on this interval, there are two other zeros as well. There's a zero here and a zero here. Okay. But that's not in the interval we were talking about. But there are two other zeros as well. Now, be careful when you interpret the intermediate value theorem. Okay, again, if A and B are not opposite in sign, it does not necessarily mean that there is no zero between A and B. We could have just picked some pretty bad points. Okay, so in this graph here, we have this point A is above the graph. This point B is below the graph. And so the intermediate value theorem says there has to be a C in between where it crosses. Okay, but I could have chose an A to be over here. right? And then A and B would have been both under the graph. They would have been both negative. But we would still have this point. So I just chose 2 points that weren't good. Okay? Now, the boundedness theorem. In this case here, it says, let f of x be a polynomial function of degree greater than or equal to 1 with real coefficients and with a positive leading coefficient. Suppose f of x is divided synthetically by x minus c. Again, just like x minus k, so x minus c. A, if c is positive and all numbers in the bottom row of the synthetic division are non-negative, then f of x has no zero greater than c. So let me say that again. So if we have a polynomial function with real coefficients and a degree that's at least 1 and has a positive leading coefficient, then if we divide synthetically by some x minus c, okay, if c is positive and all the numbers on the bottom row of our synthetic division are non-negative, then f of x has no zero that's greater than c. Okay. B, if c is negative and the numbers on the bottom of the synthetic division row alternate in sign, with 0 considered positive in this case, or negative as needed in order to make it work, then f of x has no 0 less than c. Okay, so here's the proof. Okay, so we're going to outline the proof of part A, and the part B is very similar to this. So here's the thing. So the division algorithm, we say that f of x, if it's divided by x minus c, then we're going to have, for some q and some r, we're going to have this. Okay, so we know that to be true by the division algorithm. Now, where all coefficients of q of x are non-negative. Okay, r is greater than or equal to 0, and c is positive. Okay, so this is our setup. Then x minus c, okay, if x is greater than c, then x minus c is going to be positive. Since we know that q of x is positive, and r is also non-negative, okay, then we know that f of x is also positive, because this is non-negative, and this is positive, and this is positive, so we should get something that's positive. Okay, because the lowest this can be is 0, and we're adding 0 to something that's positive, so this has to be positive. So this means that f of x will never be 0 for x greater than 0, or excuse me, for x greater than c, which means what? There's no other 0. Okay, so that proves the theorem, or that proof proves part A. Okay, so show that the real zeros of this function f of x satisfy these conditions. A, no real zero is greater than 3. Okay, so what do we do? Well, we're going to take x minus 3 then. So if this is greater than 3, we're going to use x minus c, where 3 is equal to c. So we're going to use x minus c. We're going to use synthetic division and see if we get what? Non-negative values in the bottom row. Okay, so we're going to divide by x minus 3 using synthetic division. And look, we get all non-negative values here. And since we get all non-negative values, then we can conclude that there are no zeros greater than 3. Okay, so there's no zeros greater than 3. Okay, so there's no real zero. There's no real zero is greater than 3. So past 3, there's no zeros. Okay, there might be zeros before 3. Okay, but there's no zeros bigger than 3. Okay, now show that there's no zero less than -1. Now here C is negative, so we're going to be less than. We want to look less than. So now we're going to use x plus 1, right? X minus c. We're going to use that. We're going to divide by x minus c again. In this case, it's going to be x plus 1. And then we're going to look at the bottom row and see if we can get alternating signs. Okay, and look, we start with positive, negative, positive, negative, positive. So they do alternate signs, which means there are no zeros less than -1. That's it. Now here it says approximate the real zero of this function. Okay, approximate the real zeros of this function. Okay, so let's do that. So the dominating term is x to the 4th. So the graph will have end behavior that goes in the similar direction, right? They go in the same direction, and it's positive. Okay, so it's going to look something like this. Okay, both tails are going to go up in the left and the right. There are also at most 4 real zeros because the degree is 4. Okay, so we have at most 4 real zeros. So it will cross the x-axis at most 4 places. Okay. Also, we know that the intercept, the y-intercept, is at -1. Okay, because f of 0 equals -1. Okay, and because the end behavior is positive on the left and the right, by the intermediate value theorem of f has to have at least 1 0 on either side of x equal to 0. Okay, so that means we're going to have at least 2 zeros, because since we know the y-intercept is at -1, right? And so we know that it's -1 at 0, and we know that it's going to be positive eventually on the left, and it's going to be positive eventually on the right. Then the intermediate value theorem says that, hey, there must be at least 1 0 between 0 and -infinity and 0 and positive infinity. So that's where we're going to use our graphing calculator. Okay, so the graph below shows that there are 4 real zeros, right? So we got 1, 2, 3, 4. Okay, and then we use the table indicates that they are between -1 and 0, 0 and 1, 2 and 3, and 3 and 4. Okay, because of the sign change, right? We're using intermediate value theorem here. So from -1 to 0, it changes from positive to negative, right? So there has to be a 0 here. And then from 0 to 1, it changes from negative to positive, so we have to have a 0 here. And then from 2 to 3, it changes from positive to negative. And then from 3 to 4, it changes negative to positive again. Okay, so we know the zeros are going to be between those numbers. So now what we're going to do is we're going to use our calculator. So using the capability of the calculator, we can find the zeros to a great degree of accuracy by using what's called the zero option. or the 0 function on your calculator. So what you do is you use the 0 option, and then it'll ask you to pick a left endpoint, or excuse me, a left bound, right? So you just pick a place over here and pick a right bound over here on this side of the 0, and then a guess. And then so of course you just put the cursor here and just pick something in between, and then the calculator will calculate where the 0 is at. Okay, and you can do that for each one of these points. Now, examining a polynomial model. Okay, so now modeling data. So when we talk about modeling polynomial models, we're going to start with data. So here's the data. Okay, so this is the number of transactions in millions based on the year, and this is the transactions on a bank debit cards for selected years. So here's the data. Okay, and so here we use x equals 0 to 1995. So this is our beginning point. So x equals 0 equals 1995. So x represents the number of years after 1995. Okay, so this would be 2012. 2012 would be what? 27 years after 1995. So x would be 27 in this case. Okay. Okay. Now, let's plot the data. So here's the data. So we plot the data on the calculator. And again, I could show you how to do that in class. Just ask me and I'll show you how to plot the calculator on your, oh, never mind. We're not using graphing calculators on here anyway. But you could do this on, on a graphing calculator, and you plot the data. And then you use the quadratic because it looks like this might be a quadratic, like a polynomial type function. Okay, so you plot the points. Now, since this looks like a quadratic function, we're going to use quadratic regression on the calculator, and this will actually automatically give you the coefficients that you plug in. And then what you could do is you could plot the line. So this is the actual line that they plotted, and see how nicely that line fits the data. So that's what we call regression, or modeling the data. So this is when we model the data, we're trying to find the best curve through the data. So here we used a quadratic equation, okay, to best. Then once we have the line, then we can predict things. We can say, okay, well, what would be the number of transactions here in this year or this year? And so we can use the model to tell us. Okay, so there's the model. And then we could repeat the thing for a cubic function. So now we do go to cubic regression, and we find, oh, here's one that fits a cubic, right? It could be a cubic function. Okay. And there's the best fitting cubic function. Okay. Or we could use a quartic function, right? A fourth degree. Okay, and so this is the best quartic function that models the data. Okay, so sometimes there's more than one function we could use. We have to use what's appropriate based on what we know, expert opinion, and things like that, right? Now, the correlation coefficient is what we're also going to use to help us look at which graph best fits the graph. Because if you look at these, they all look like they fit really well, right? So which one? So that's where the correlation coefficient comes in, R. And that's also one of the outputs on the calculator. That measures the strength of the relationship between the two variables. Okay, R and R squared are both used to determine how well our regression model fits the set of data. Okay, so if R squared is 1, that means it's a perfect fit. Okay, so the closer to 1 R squared is, the better the fit. Okay, so if we use the R squared value, right? So if we look at these R squared values, which we got from the calculator here, So if we look at the R values, which one is closest to 1? Well, it looks like the quartic. The quartic is closer to 1. Okay, 9986, 9988, 9998. So this is closer to 1. So the quartic function is going to be the one that best fits the data based on the correlation squared. Okay, so now in part D, we selected the quartic function as the best model based on the comparison of R squared values of the models. But in practice, remember, however, the best choice of this model should also depend on the set of data being analyzed as well as the analysis of trends and attributes. For example, we're talking about transactions here. Okay, there may already be a distribution or a curve that's used in the industry, right? So knowing more about the data is going to be important. It's not just about looking at R squared values and just going with the highest R squared value. It's more than that, okay? Okay, so that ends this section. So again, please make sure that you go through and understand what we're doing here. Understand the examples, understand the calculator, but again, we're not using graphing calculators here, but make sure you understand what's going on with the modeling, okay? Make sure you understand what's going on. We're not going to be doing it in the calculator, okay? We're not using calculators in this class for that. We're not using graphing calculators, but you should still be able to know what's going on and why, how we use this information, okay? So, again, if you get stuck on something, if you're working through the homework or anything like that, bring those questions to the class. Email me. But again, make sure you bring those questions to class, and we'll work through these in class. If you get stuck on the homework, bring those to class as well, okay? So until then, have a great day. Okay, guys, come and eat.